Yeah, this is just a kind of summary of the work that we've been doing as part of one of the NESP projects in the last, well, this year and kind of the 2 years before. So the project is Extreme Climate, Hot. The name is Dry, Wet, Hot, and Dry, which I always get confused about. There are various components in the project looking at drought, but our component is looking at kind of the drivers that influence the swings between extreme wet and dry conditions. So I'm just going to talk about two kind of parts of the work. The first part was out in a paper that came out last year in ACCESS, which was evaluating teleconnections of ENSO, IOD, and SAM to Australian rainfall. And this is just seasonal rainfall in the CMIP6 models. And the second part, which is work in progress, is kind of then looking at projections of ENSO, IOD, and SAM change. Like I said, the motivation behind this is kind of looking at the drivers of the swings between interannual and seasonal rainfall variability. How well do the CMIP6 models simulate these teleconnections? How are these projected to change? Also, we know that the models are quite noisy, even within the model ensembles and between the different models. Is there any model consensus on future change? Can we kind of figure out what's the forced signal versus internal variability? And then eventually, which is hopefully in the next month or two, we'll start looking at what, given the model consensus on driver changes, what can we say about the most likely rainfall future change based on all the above results? For this, we are using historical SSP 370 and SSP 585 output. And we're looking at all ensemble members for this. So I should say SSP 370 and 585 are quite similar in terms of their projections, as I'm sure you know. Okay, so just the first part, I'll just go quickly through this, as I think some of you may have heard this before. So this is just evaluating the teleconnections in the historical period, and this is the paper that came out last year. So we looked at ENSO, IOD, and SAM separately and for each season. So what I'm showing here, for example, is observations on the top. So you've got JJA, SON, DJF, and MAM. So these are AGCD observations. In the middle row, we've got the CMIP5 multi-model mean. And in the bottom row, we've got the CMIP6 multi-model mean. So we wanted to see if there was kind of any improvement or change between CMIP5 and 6 for this. So I guess the main thing that pops out is that for JJA and SON, there's a noticeable improvement for the multi-model mean. So a bit more, so it's stippled where there's more model agreement. I should say also this is just the straight correlation between Nino 3.4 and seasonal rainfall. So yeah, JJA and SON, there's quite a bit more stippling. The teleconnection seems stronger overall, closer to OBS, which is good. So our conclusion from this bit is that CMIP6 overall has improved in the simulation of winter and spring teleconnections. In the paper as well, we looked at the El Nino, La Nina asymmetry, because we know that La Nina's got a stronger teleconnection. And also we looked at the difference in the CP and EP teleconnections, because the CP El Ninos generally have a stronger impact. And what we found from this was that the models in general do capture this asymmetry generally, but there's no noticeable difference between CMIP5 and CMIP6. There's still quite a large spread of teleconnections. So a bit more uncertain. For IOD, just looking at winter, spring, again, there is quite a significant improvement in the CMIP6 multi-model mean, which is good to see. We looked at SAM as well. For SAM, it's kind of the opposite story because we've actually got an overall worsening in the teleconnections in CMIP6. So for example, if you look at SON and DJF, there's a bit less stippling in CMIP6. So there's a larger spread in the kind of model behavior, so less agreement. And, the teleconnections are a little bit weaker as well, which is not great. And I think a bit surprising because I think overall the simulation of SAM has improved, but somehow the teleconnection to Australian rainfall has gotten worse in CMIP6. And I should say for these maps, we just looked at the first ensemble member from each run. So that's just the first bit. Basically what I've said, improvement in ENSO IOD in springtime. SAM has gotten worse. And then the other thing we kind of looked at as kind of a side note was looking at the spread in the teleconnections among ensemble members. And this was kind of scary because there is a huge amount of spread. So for example, just showing for ENSO, this is the correlation between Nino 3.4 and all Australian rainfall, springtime. This solid line is OBS, and you can see that for some models, there's a huge amount of spread in the ensemble members. The red dots are showing the first member that, some people normally use in their analysis. So just showing, kind of highlighting the point that depending on what metric you use, depending on what you're looking at, there's a big spread. So especially for the downscaling folks, I guess be careful, like which ensemble member you're using. It might be great in one metric, not great in another metric. Yeah, so that's kind of the message from the first part of the study. And obviously a lot more detail in the paper. We've got a huge appendix with maps of all the models and all the correlations. So if you're interested, you can have a look at that. A second part of the work is still being written up as we speak. And this is kind of looking at the changes in ENSO IOD and SAM going into future, looking at the change in certain properties, in particular amplitude and frequency. So just starting off with ENSO, and here I'm using Nino 3.4 DJF. So here we've split it up into phases. So El Nino on the top, La Nina on the bottom. So there's quite a bit going on here. I'll explain it in a bit of detail. So on the left-hand side is the change in amplitude distribution. So in gray or black, we've got the histogram of historical Nino 3.4 amplitudes and just the absolute value. In the orange, we've got SSP 370, and in the red, we've got SSP 585. So that's up top for El Nino and bottom for La Nina. The hollow bars indicate that the change in the means of the distributions are not statistically significant. I think there's like a use 90% here. On the right-hand side is the change in the number of events, so the frequency. So again, historical is black, orange is 370 and red is 505. So here there is a significant increase in the number of events for both El Nino and La Nina. And I should say the way I've defined the events is if the index is larger than 0.75 of the standard deviation in each period. So calculating the threshold is different for the historical and the future periods. And here just again quickly looking at the change in standard deviation between future and historical, and you can see that I think this is like 75% of the models indicate an increase in standard deviation. So generally an increase in variability. And I think others like Chai have looked at this before as well. So that's kind of looking at the change in the means of the distributions. And then we also want to know how can we, how much of this is forced, how much of it, what is the spread, what will we get if, just from natural variability or internal variability. So here is the spread of the change in amplitude of the indices on the y-axis, and then on the x-axis is the change in frequency. So the left being, fewer events, the right being more frequent events. And to kind of get an idea of what we would expect from just internal variability, we looked at the PI control runs and just took 2 random periods from the PI control runs and calculated the change in that and said, okay, well, what's the range that you get from just calculating the spread in that? And those are shown in the gray boxes here. So I should say here, again, orange is 370 and red is 585. You can see the whiskers are kind of the spread in the ensemble members. So again, there is a huge spread in the projected change of amplitude and frequency. And I think the multi-ensemble means are the stars, and the squares are just where there's like one member. So yeah, so surprisingly for El Nino, the internal variability is quite big. In fact, it's twice as large as the La Nina internal variability. I'm not quite sure why this is, or if it's kind of a known thing, but it's interesting. So then from here we calculate, well, what's the fraction of models using just ensemble means? What's the fraction of models that kind of lie outside the box, outside the boxes? So we've got 4 categories. We've got amplitude increase up here, amplitude decrease, frequency increase, or frequency decrease. So you can see for El Nino, there's only like a couple models up here that are in the frequency increase kind of section. So that's kind of roughly 6% of the models saying frequency increase, 6% of models saying amplitude decrease. These are the ones that are just kind of in the edge of the box here. Apparently there's one that's amplitude increase, but I don't know. This might be a bug. But again, for El Nino, not a huge amount of kind of lying outside the internal variability box. For La Nina, there's a bit more of a stronger signal. So maybe closer to 20% of the models saying amplitude increase, and about 10% kind of saying lying in this box, in this frequency increase here. So I guess this is kind of just a way of trying to gauge what's forced versus unforced. If anyone has any suggestions on alternative methods or how to improve this, I'd love to hear. And similarly for IOD, it's a bit messier, like the change in standard deviation is half of the models are saying increase and half are saying decrease. In general, there is a negative, so there's a decrease in the amplitude of the indices. So in general, this is saying the events are getting weaker. No significant change in frequency. And this is just for the overall distribution. Again, looking at the scatter plot and bar plots, there's a bit more of a forced change here for IOD compared to ENSO. But interestingly, for positive IOD and negative IOD, the directions are quite different. So for example, for positive IOD, we get 40% of models saying amplitude decrease, and maybe 25% of models saying frequency increase. So weaker but more frequent events. And there is a weird cluster of models down here at the bottom right quadrants, which are these models. Don't know too much about individual models, so if anyone knows that anything weird about these models, please also let me know. I'm not quite sure why they're kind of separate from the rest of the group. For negative IOD, there's a bit less consensus on amplitude change. So, some 25% saying going up and 20% saying going down. But there is quite a larger number saying frequency decrease. So for positive IDs, it's saying weaker, more frequent. For negative IDs, it's saying not sure about amplitude change, maybe a decrease in events. So not quite sure what the reason for this is. It could be to do with maybe the warming patterns or the bias. I'm not sure. I'm going to try look into this a bit more this week and next week. Again, any suggestions, please let me know. For SAM, SAM changes are quite robust, and I think this is kind of linked to the mean state change in SAM in the models. So the models are saying there's a significant shift towards stronger events, but also weaker events. And this is, I should say, only for springtime. I'm not sure about the other seasons. And again, most of the models seem to be saying an increase in variability. So again, looking at the same scatter plot, so the change in SAM seems to be the most robust and kind of most, positive and negative SAM have this similar, quite similar response. So we get around half of the models saying, yes, we're going to get stronger events, but also less frequent, maybe. So it's a bit of a mixed bag, I think, in terms of projections. There's no kind of clear message popping out. Also looked at whether there was any change in frequency of these concurrent events, so like a few phases happening together. So, I mean, there's a lot happening here. I won't go into detail, but basically this is like La Nina plus negative ID plus the various phases of SAM, La Nina neutral ID and various phases of SAM. And then on the other side here is El Nino positive ID and SAM, El Nino neutral ID and SAM. Yeah, so I mean, not a huge amount of significant change in frequency. There's a few here, but in general, it's noisy. There's not a big significant change in any of these, concurrent events. Except, yeah, well, the El Nino neutral ID, neutral SAM seems to be the largest change here. So more frequent kind of El Ninos, which is what we saw in the previous plot as well. And then because this was of interest to some NESP people, NESP stakeholders, we also had a look at whether there's any change in consecutive phases. So 2 or 3 or more El Ninos, here, La Ninas, positive ID and negative ID. And this is just using, again, the ensemble means. So each model is weighted separately, evenly. Not a huge amount of change, I'd say. Maybe a little bit of increase for El Nino, La Ninas in the future. A bit of an increase for positive ID events. Maybe a decrease for consecutive negative ID events, but it's not a huge change, I would say. Yeah, so that's kind of the gist of the paper. It's just kind of summarizing what I've said. Hoping to get this out soon, and then the next step will be looking at kind of what are the associated rainfall changes. Yeah, that's it. Thank you. Sorry, it was a bit short.
Thanks, Christine. Any questions? Gemma, you got your hand up.
Yeah, so just to clarify, you got generally an increase in frequency, but also an increase in consecutive events. Can you explain how those two ideas fit together and they're not contradicting? That it's not implying things are both longer and shorter?
Yeah, so I mean, let me see if I can. So you're talking about like El Nino events?
Yeah, you're getting an increase in El Nino and positive IOD. I guess there's a slight decrease in.
Yeah, I mean,
There's an increase in La Ninas as well. So both El Ninos and La Ninas increase in consecutive events, but also you showed an increase in frequency.
Yeah, I mean, I would say this increase is really small. So this is literally the number of events over a 65-year period. So it's literally going from like 2.5 to 3. So it's not a huge, like I wouldn't make any strong conclusions from this plot really, because there's a bit of uncertainty as well. And I think, yeah, it's not a strong signal, I would say.
You'd say the frequency signal is stronger.
Yeah.
Okay, thank you.
Nicola, I think you were next.
Thanks, Christine. Cool talk. I have a question about the one where you look at the percentage of times you go outside of the internal variability, these ones.
Yeah.
So is that calculated as every time an ensemble member goes outside, or is that when the means go
When
outside?
the means, yeah, just the means.
And then why would it not make more sense to use the ensemble members
Yeah, so initially
individually?
I
Yeah.
had done that, and then I was like, oh, I've gone through so many iterations. I think, yeah, because some there's some models with like 50 members, and then there's some single. So I thought maybe it's better to weight every model evenly. But I'm not 100% sure that's the best way to go. Yeah.
Yeah, I only asked because I mean, I guess maybe you're down weighting how much they go outside in this case, because like the ones where you do take the means, you kind of expect them to go back inside the internal variability the more members they have.
Yeah.
So
yeah, I mean, you definitely get more of a, that the fractions are bigger when you use all the members. But again, it was like, is that way better than this way? I wasn't sure. So,
yeah, I see your point.
Initially I started off using each member separately, and then only 2 weeks ago I've changed it to use the ensemble mean. So yeah.
Cool, thanks.
Shane?
Hey, thanks for the great talk, Christine. So I suppose 2 questions. One, I might have missed it, was just how many years of data when we're looking at the projected data or the historical, how many years were you looking at for each?
Oh yeah, so I was using the last 65 years of each.
65, okay.
Yeah.
All right, and the second question was about I suppose the model representation of ENSO itself, or the concurrent events, and how realistic it is. You said the models are averaging like 2.5 consecutive events in 65 years, I think.
Yeah.
Is that a realistic range? Is that something?
I think so. Like, I don't know if we're talking about the recent like triple La Nina. I think it's happened, is it 2 or 3 times in the since 1900 or so, I think. Is that right?
Yeah, I think since 1950s it's 4.
Yeah. Oh, okay.
I don't, yeah, that's just from the top of my head. I could be wrong. I was just I suppose I'm curious if I wanted to believe, like if I wanted to believe this, I suppose there's that aspect. You kind of go, well, how many of the models kind of get the observer relationship well, and I wasn't sure if you just looked at that.
Yeah, so this is it's interesting because like last year Chai and group had a paper on the triple La Ninas and projections of those, and they selected, I think it was like maybe 10 or 12 models that I think they simulated some process in the Pacific well. And those models showed quite a large increase in the frequency of these triple La Ninas. So I think it depends on the models you're looking at, and like if you select a certain models that do something well, then it might very well give you a different number.
Yeah.
I guess the approach here is we just consider all possible futures. So yeah.
When I think about this, I think about like CM2, which is like really biennial, and it's probably, I don't know, you could probably hit it hit
Yeah.
with 50 nuclear bombs or whatever, and it's still going to be really biennial. So,
Yeah.
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 Okay.
I think,
All right. Thank you very much.
Thanks, Shane. Yeah, I think in general the models are still pretty biennial, aren't they? So
Yeah,
this-
I'm not too sure. I know some of them are, but I know some are more realistic. But I'm not sure on the details of that. They're just not popping to the front of my mind. So I
I'm
asked.
guessing this would be an underestimation, if I were to guess. So.
Umpa, you got your hand up as well.
Yeah. Can you hear me?
Yes, we can hear you.
Yeah, good. I turned on my video, but I'm still black. But anyway,
Is this the bureau
thank you.
laptop? All the cameras are
Yeah,
broken.
thank you very much for the interesting talk. So the first question is there any kind of improvement in terms of the relationship between ENSO and SAM in CMIP 6? When we had a look at CMIP 5, and there was, no, the relationship was all over the place.
Yeah.
So I wonder whether there is some kind of improvement in that.
Yeah, so this is interesting. Actually, I haven't shown here, but I was asking Ghislaine the other day. So I have a plot somewhere looking at the correlation between NINO 3.4 and the SAM index. But I think I'm correlating the wrong seasons because I'm correlating springtime SAM with DJF NINO 3.4 and looking at the change in the correlation between historical and future. And it's really interesting because the models that start off with a weak correlation tend to increase the correlation in the future. And then the models that start off with a stronger correlation tend to decrease in the future, which is really weird. And I don't understand it, which is why I didn't show it here today.
So there
yeah,
is some relationship in
yeah,
some
not,
models.
Yeah, so it's not answering your question, but it's just there's just a weird relationship which I don't understand. So.
I see. And my second question is, like, you showed that ENSO amplitude and frequency change, like not necessarily kind of similar to what IOD or SAM shows. Like SAM and IOD, the frequency decrease and amplitude was SAM was increased, but IOD I just forgot. So is there any kind of indication that actually ENSO and IOD or ENSO and SAM relationship got weaker?
Yeah, again, so
Not necessarily consecutive compounding events, but just year to year
so I
variability.
think it is a mixed bag. I think half of the models are saying increase and half increase in the correlation, and then half are saying decrease in the correlation, if I remember. Yeah, but I don't quite understand that result quite yet. So maybe I'll have a chat to you. We could maybe next week I can come ask you about it. Yeah, it's quite odd, the change in correlation between the drivers. There seems to be this dependence on the initial starting value.
Right. It seems like there is a large scope to improve in CMIP 7. Is there a plan to actually diagnose how these kind of large scale drivers will be differently simulated in CMIP 7? I mean, it's not to the question to only Christine, but to anybody who is working on CMIP 7. Like, is there a kind of standard matrix to include the evaluation of these kind of correlations between ENSO and other aspects and so on?
I hope so.
That's kind of part of the ECM val tool and stuff. And wasn't
right.
that, Christine, wasn't that what you guys were doing at the
Yeah, well, that's one aspect of it. So we would like to have kind of a more streamlined evaluation process this time around. And yeah, ESMWG tool looks like it'll play quite an important role in that if we can get the recipes and everything going. So I'm just showing you these plots, which are, again, I've just made them last week. They might be wrong, but it's weird. So this is correlation between Nino 3.4 and DMI on the left. And I've sorted them according to historical values. So cross is historical, and then the dots are the change. And then on the right-hand side is the correlation between Nino 3.4 and SAM. So it seems like the models that start off with a weak correlation, kind of in both cases, tend to increase their correlation in future. And then the ones that start off strong tend to decrease their correlation. But I don't understand this result.
So the dots are a change and the crosses are the original raw correlation value?
Yeah, I think so.
So it looks like everything has no correlation in the future, but some of them have correlations in the historical run.
Ah, yeah, because we're looking at the difference. Yeah. So yeah. So generally a decrease in correlation.
Christine, if I was curious, I agree with that interpretation. I wondered if you were to get different ensemble members from the ones with the high correlations or the low correlations, if you were to look at different ensemble members, whether on average they're kind of around zero.
Yeah.
You know, and some are positive and some are negative, and it's just kind of tracking you back towards what that.
Yeah, agreed. That was my next question.
Yeah. So again, here I've just taken the ensemble mean.
Mm.
Yeah.
Oh, it's ensemble mean. Okay.
Yeah.
Yeah, well, I thought it might have just been the first. Sorry.
Yeah.
Awesome.
Yeah.
That's really interesting.
Sorry, Shane.
No, it's just saying it's really interesting. With no questions.
Are there any more questions?
One more quick follow-up on that same thing. Just
Please go.
yeah, that's the ensemble mean, but I'm curious if you get exactly the same plot with each ensemble member. Because if so, that would tell you you're picking up something spurious in the historical that's relaxing back.
Yeah.
And if all the ensemble members doing something in the historical and still doing the opposite in the future, that would tell you more about the model.
Yeah, that's a good idea.
Nicola?
Yeah, just on that, because they all have different ensemble sizes, right? So maybe the ones with the bigger differences that aren't averaged out are the ones with the small ensembles, and the ones that are closer to zero are the ones with the large ensembles, which would fit with what was just discussed. So yeah, maybe all ensemble members would kind of clarify whether that's just what it is or not.
Yeah, that's a good idea.
Haroon? If you are speaking, Haroon, we can't hear you.
Can you hear me now?
Yes, we can hear you now.
Yeah, for some strange reason, I have to open the lid of my book to be honest. Anyway, so hi, Christine. Sorry, I actually missed much of your talk, but it looks interesting. You know, other people are talking about it. So, have you got a signal that in that forced, and you know, so you're saying that ENSO frequency has increased, and is that right? Or
yeah, so I guess there's two ways that I'm measuring the change here. It's the change in the overall distribution, in which you see this significant increase in frequency. Then when you look at how many models are actually outside the box of internal variability, there's not many. So
yeah, and what about amplitude? Is it getting stronger?
So amplitude, it is. Let me share again. So if you look at the shift in the distribution, it is getting stronger, but it's not like significant. But by definition, because I've got two thresholds for for picking events. So by definition, if the standard deviation in the future has increased, then the events that are being picked up will have larger amplitude, because otherwise they wouldn't be picked as events. You know what I mean?
Okay, yeah. So the reason I'm asking this because I looked at the ESM 1.5 large ensemble, how the ENSO amplitude especially changed in SSP 370 scenario with respect to historical. So what I found was that the amplitude has increased, but that increase is actually less than the inter-ensemble or the intra-ensemble variability, or the,
Yeah.
it's for the ensemble members.
Yeah.
ESM 1.5.
Yeah.
So the variation across the ensemble of amplitude is actually larger than the ensemble average piece between a historical run and SSP 3.70.
Okay, so that's kind of consistent here, because like there is an increase overall in amplitude, but it's not significant, and also it's falling a lot within the kind of internal variability box.
Okay, yeah.
I think that's consistent, which is good.
Yeah. So this was some work that that was published actually in Frontiers in Climate in last year, I think.
Okay.
And so your frequency is increasing. Does it mean that the ENSO cycles periods are getting shorter? Say shifting from 4 to 3 years or something like that?
Yeah, I haven't looked at the periodicity change.
Okay.
A good one.
All right. Thanks.
Thanks, Arun.
Thank you. Any other questions? If not, then thanks again, Christine, for a really interesting talk, and thanks everyone else for the discussion.